This is the lab number 3, the black hole lab for Physics 2211. So the purpose of this experiment is to find the mass of a given black hole in part 1 and calculate the trajectories of two objects orbiting around it, the planet and the ship, in part 2. So I was able to calculate the mass of the black hole and the velocity needed to maintain an orbit around it using GlowScript. So two fundamental physical principles. The force of gravity equals g m1 m2 over r squared. And the centripetal force is mv squared over r. The gravitational force is the only force that's acting on these objects in all of these scenarios. And the centripetal force is the force that acts on the body in an orbit. Specifically, in a circular orbit, r is the radius. In an elliptical orbit, r is the will be the length of the major and minor axes. And the initial conditions for part 1 are the gravitational constant, the mass of the star, which is a given, delta t, which is meant to be 1 day in seconds, and t equals 0. When you find the mass, you take you calculate delta v and delta p, and then you say dp dt is delta p over delta t, which works because it's a short time interval. And fnet is dp dt, so dp dt parallel is the dot product of fnet p hat, and dp dt perpendicular is the cross product of those, and so you get fnet parallel and fnet perpendicular, and therefore you get the mass of the black hole, which ends up being 9.23. In my case, with my seed, it ends up being 9.23 times 10 to the power of 33, which feeds into the initial condition for part 2. Same G, given planet mass and a given ship mass, delta t equals 1 second and t equals 0, which is just the initial time. And then in part 2, we have to find the gravitational forces on the planet from the black hole and the ship, and then on the ship from the planet and the black hole. And we apply the position update formula and the velocity update formulas to get the orbit of the ship and the planet around the black hole. So our assumptions for both of these are that the givens are like reasonable and not weird, and that the time step is short enough to model a non-constant force, because if the time step is too long, then the force will be like we're modeling it as a constant force. So if the time step is too long, it'll be too much constant force. Sources of error. My code could be bad and weird. It could have something like physically impossible in it. And also, if the time step is too large, the results will be inaccurate because the force is, in reality, the force is non-constant. And if the time step is too large, we'll be modeling it as a constant force. In my analysis, you should discuss how the net force and its parallel and perpendicular components are different from the rate of change of momentum in its parallel and perpendicular components. Well, since by Newton's second law, Fnet equals dp dt, these are the same, so their components are also the same. And if we want to enter into an orbit around the black hole, I was just using trial and error for this. V equals 0.1c, 0.1c0 works. It gives this orbit. The spaceship is actually in purple, so it gives this elliptical orbit. And it doesn't crash into the planet. The orbits do intersect, but they don't like intersect at the same time, which would mean that it crashes into the planet. So in this lab, in part 1, I found the mass of the black hole by reversing the equation for gravitational force. We knew Fnet and needed the mass. And then I used the dot and the cross product to calculate the parallel and perpendicular components of Fnet. In part 2, I used the gravitational force equation and velocity and position update formulas to calculate the new position and velocity of the planet and the ship. And then I found an initial velocity that allowed the ship to stay in orbit around the black hole through trial and error.